Question 1. In the quantum mechanical model of light-matter interaction, which process involves an incoming photon triggering an excited electron to drop to a lower energy state, releasing an identical photon? Stimulated emission is the fundamental driving force of laser action. An incoming photon triggers an excited electron to transition to a lower state, releasing a second, completely coherent photon. Question 2. What condition is fundamentally required within a gain medium to achieve optical amplification rather than net absorption? Achieving optical amplification requires a population inversion. This is a non-equilibrium state where more atoms populate the higher energy level than the lower one, enabling gain. Question 3. Why is a 4-level laser system generally much easier to pump and operate continuously than a 3-level laser system? Four-level systems are highly efficient because their lower laser level is rapidly emptied, meaning we do not have to struggle to clear out ground state atoms to keep our inversion stable. Question 4. What property of laser light refers to the correlation between the phases of the light wave at different points in space transverse to the direction of propagation? Spatial coherence refers to the transverse phase uniformity across the beam. This unique properties is what allows us to focus lasers down to highly concentrated, microscopic points. Question 5. In an optical cavity consisting of two mirrors, what specific component is designed to be partially transparent to allow a fraction of the amplified light to escape as the output beam? The output coupler acts as a gateway for the laser cavity. By keeping it partially transparent, a fraction of the oscillating light is allowed to leak out as our useful, coherent output beam. Question 6. What is the relation between the minimum temporal duration of a laser pulse and its spectral frequency bandwidth according to the Fourier transform limit? Due to the wave properties of light, a shorter optical pulse in time must spread out over a wider frequency band. This absolute constraint is described by the Fourier time-bandwidth product limit. Question 7. What pulsing technique operates by periodically blocking and restoring feedback inside the optical cavity, allowing a massive population inversion to build up before releasing a single giant pulse? Q switching works by temporarily lowering the cavity's quality factor, or Q, to suppress lasing while we pump energy in. Restoring the Q factor instantly triggers a single giant, high-energy pulse. Question 8. What type of gas laser, co-invented by Ollie Javan in 1960, was the first continuous wave laser to operate, producing light at 1.15 micrometers? The helium neon laser made history as the first continuous wave gas laser. Developed in 1960, it demonstrated that sustained gas discharge can produce highly stable, coherent infrared beams. Question 9. Which physical parameter of a laser beam describes the angular spreading of the beam over long distances from the beam waist? Because of optical diffraction, no laser beam can stay perfectly parallel forever. Beam divergence measures this slow angular spreading of our wavefronts over great distances. Question 10. In an electrical discharge gas laser, what is the primary role of the secondary gas, such as helium in a helium-neon laser? Helium atoms act as efficient energy conduits. They absorb kinetic energy from passing electrons inside the discharge tube and transfer it to the neon atoms via resonant atomic collisions.